We are in Unit 10, and this is our first day, so this is Notes 1. This unit deals with parametric equations. Today we're doing parametrics and vectors, which is also motion along a curve. Back in, I forget which unit it was, we've already done rectilinear motion, which is motion on a horizontal line or motion on a vertical line. Okay, so we've already done that. If you remember from that, we had like S of t or X of t or Y of t, that each of these would represent the position of the particle, and the particle was moving either on a horizontal line or a vertical line. And then if we took the derivative of position, we got velocity. So velocity was the derivative of the position, whichever form the position was in. And then acceleration was the derivative of velocity, so acceleration was the second derivative of position. So, and we had you know, at what time is the particle at rest? At what time does the particle change direction? We had in what time intervals is the particle speeding up and slowing down? We had questions like that. We're going to have similar questions in this section, but instead of being in a horizontal or a vertical path, we're going to be moving along a curve. All right? So our curve is going to be given by a set of parametric equations. So our curve will have both horizontal and vertical position. X of t will be horizontal and Y of t will be the vertical. All right, so there are two components. In particle motion. All right, so time is going to be, t is going to represent time for the most part, for almost exclusively, but the methods and the content of what we're doing applies to other things as well. So parametric equations can be different things, but today it's going to represent motion on a curve. All right, so let's talk about this. I gave you a notes packet, so hopefully you have that out. It'll have all of our examples on it. The first thing that we need to do is talk about dy dx. dy dx is always the slope. This is the slope of the curve. Okay, and you can see that on your in the first box, your top box of your formula page there. dy dx is the slope of the curve. But remember, we're going to be given x of t is something in t's, and y of t is something in t's. All right, so dy dx is the slope of the curve, but how do you find dy dx if you have x and y both as functions of t's? Well, that's the first thing on your sheet, so let's take a look at that. dy dx is dy dt divided by dx dt. Another way to write that, so dy dx is dy dt divided by dx dt. Another way to write that is y prime of t divided by x prime of t. Those mean the same thing, all right? When you are asked to find the slope of the curve, you're finding dy dx, even if you have t's in your equations, all right? It's always dy dx. All right, now, the second derivative. What if you were asked to find the concavity, something about the concavity of the curve? Well, the concavity of the curve would be the second derivative of y with respect to x. This is where it gets complicated, and this is where kids tend to want to simplify things. If we are finding the second derivative of y with respect to x, we are taking the derivative with respect to x of dy dx, right? That's what the second derivative is. When we're in parametrics, dy dx is going to have t's in it. It's going to have t's in it. So you're taking the derivative with respect to x of something with t's in it. So you're going to have to do this implicitly. All right? We'll do some examples. But this is true. This is not equal to just y double prime of t over x double prime of t. That's what kids want to do. And that's not true. That's different. These are two very different things. So the second derivative is not that. All right? Okay. We'll be doing some examples. All right. So, yes, dy dx is the slope. The second derivative of y with respect to x is the concavity, the change in slope. All right. X prime is the velocity of the particle in the horizontal position, because x is always going to be the horizontal position. So x prime will be the velocity of the particle only in the horizontal direction. Y prime will be the velocity of the particle in the vertical direction. Okay? So you have these components. In vectors, you have these components. All right? If you just were asked to find the velocity, you're talking about a vector, all right? If you're in particle motion like this. So we're going to have a position vector. You're going to have a velocity vector and an acceleration vector, all right? So vectors. This little, I don't forget what those are called. I want to call them chevrons, but I don't know that they are. But anyway, that is vector notation. So I tend to use these for vectors, these little chevron-looking things. I should have looked up what the name of that was. I always forget from year to year. Anyway, I will use these because that's how I learned it. Okay, just know that AP accepts either these or just plain old parentheses. All right. To me, the parentheses are confusing because it looks like it's not a vector, and it is still. Even if you use parentheses, it's still a vector. So just keep in mind that these are all vectors. It has both a horizontal component and a vertical component. Each of these does. All right. The next thing on your formula sheet is called the magnitude of displacement. And yes, there's a formula here, but I'd rather just, I'll introduce that in a problem to you, and it'll make sense. It looks very complicated here, but it really is not. The speed of the particle. The speed of the particle is the same as the magnitude of the velocity vector. Back when we did horizontal and vertical motion, the velocity, the speed, was the absolute value of the velocity. It was always the absolute value, okay? Interestingly enough, the notation for magnitude is absolute values. So the speed will be the magnitude of velocity. In this case, though, velocity is a vector. So it's not just the positive of each of these. It is the distance. It's the magnitude. So it's the distance of that vector. Okay? Again, we'll be doing an example of this. I think that makes sense. Length of the arc, or total distance traveled. I would like to introduce this. I would like to show you where this comes from, because we can. Because I know that you can do this. All right. So I'd like to begin with our old arc length formula. This was our old arc length formula. This was the one that we developed ourselves using the Pythagorean theorem. That was the length of a curve. This is length of a curve. The question is, what is this formula if we're in parametrics? What if x and y are both functions of t? Are both functions of t? Then what happens to this thing? Okay, well, let's work it out and find out. So the length of that curve will be, all right, dy dx, we already said what dy dx is. Dy dx is dy dt divided by dx dt, right? Yep. Okay. So this is, well, I shouldn't, I want to get a common denominator. Okay. I'm going to get a common denominator. So this is going to be dy dt squared divided by dx dt squared. So my common denominator will be dx dt squared. 1 is dx dt squared divided by dx dt squared. So inside the radical, I'm going to have dx dt squared plus dy dt squared divided by dx dt squared. And again, that's all inside that radical. Okay? Now we have the top radical divided by the bottom radical, right? And the square root of dx dt squared is the absolute value of dx dt, which is going to be positive, so it's dx dt. All right. Now I have this. I have that radical still. I'm dividing by dx dt, which is the same thing as multiplying by dt dx. Look at that. What happens to the dx's? They cross out. They cancel out. Now, the a and the b here, now we're in a dt, right? I'm going to keep this a and b, but these are times now. They're not x values. So I kind of hate to keep the same a and b because it makes it look like they're exactly the same as they were up here. But we went from x equals a to x equals b to now these are times, all right? So it depends on your problem, but those are times, just like they should be. Okay, so this is the length of a curve. Okay, now looking back at our speed, look at our speed. Look at that square root of the speed, and look at it in this square root. They're identical. So this is the integral from time a to time b of the absolute value or magnitude of the velocity, which is also speed. All right? Okay? Now, another thing to remember with these problems is we're going to be using the fundamental theorem of calculus. If we know velocity, then we can get position if we have a position given to us. If we know acceleration, then we can get velocity if we have an initial velocity given to us. So the fundamental theorem of calculus is useful with these problems. Okay, let's take a look at some problems. I will tell you that usually kids don't mind this stuff at all. Okay, so nothing to be afraid of. This stuff is all right. Okay. All right. I'm grabbing a couple of colors here. An orange, pink. All right. All right, let's say we're given the parametric equations. X is 2 square root of t, y is 3t squared minus 2t. Part A, find the slope of the line tangent to the curve in terms of t. So slope is always dy dx, always. When we're in parametric mode, that means dy dt divided by dx dt. Good old Leibniz's notation makes it all look so right algebraically. dy dt is 6t minus 2. dx dt is, this would be 2t to the 1/2, so 1/2 times 2 is 1, t to the negative 1/2. Okay, if this was a multiple choice question, this is 1 over square root of t, so I would multiply top and bottom by square root of t. And I'd get 2t minus 2 square root of t over 1. Okay. Another thing I could write that as, I could distribute that square root of t in, and then I would get 6t to the 3/2 minus 2t to the 1/2, or square root of t there. Okay. All right. Sometimes it's beneficial to do this if we do have to find the second derivative. Okay. All right. Second derivative time. Of everything in this whole section, probably this is the thing kids dislike the most, which I find really funny, because we're doing some very complicated things elsewhere, but for some reason that's not a problem. Finding the second derivative, kids just want to do it simple, and it's not that simple. They want to come up here and just take the derivative of this divided by the derivative of that, and it's not right. The second derivative is the derivative with respect to x of dy dx. Well, we just now found dy dx. dy dx is right here. All right? So we're going to take the derivative of this with respect to x. So we just use implicit differentiation. Not a problem. Take the derivative with respect to t, and then multiply by dt dx. That's all there is to it. So take the derivative with respect to t. So 3/2 times 6 is 9. That's 9t to the 1/2, okay? Minus 1/2 times 2 is 1, t to the negative 1/2. So that's the derivative with respect to t. And now we just multiply by dt dx. All right? Now, what is dt dx? We don't know dt dx, do we? But we do know dx dt. So what can we do? dt dx is 1 over dx dt, right? So this is the same thing as 9t to the 1/2 minus t to the negative 1/2 times 1 over dx dt. And we do know dx dt. It's right there. So this is 9t to the 1/2 minus t to the negative 1/2 divided by t to the negative 1/2. Say stop. Not multiple choice answer though. And I run out of room. And I know I'm going to need this space here, so I'm going to come up here, you guys. Hate to do that, but I'm going to come up here. I think I'm going to multiply top and bottom by square root of t again, or t to the 1/2. I'm going to multiply top and bottom by t to the 1/2. Let me see if I can squeeze that in. Multiplying by square root of t again. So this will be 9t to the first minus 1. That would be the MC answer, because it's much simpler than this thing, right? Okay. Do that. Do a few of those. There's a few on your homework, all right? And do a few of them, and it will make sense. All right. Example 2. Given the parametric equations 4 cosine t and 3 sine t, write an equation of the line tangent to the curve at the point where t is 3 pi over 4. Well, the first thing we need to do is find the point, because we're writing the equation of a line. So the point is when t is 3 pi over 4. So the x-coordinate will be 4 times cosine of 3 pi over 4. Cosine of 3 pi over 4 is negative square root of 2 over 2. So x will be negative 2 square root of 2. Y will be 3 sine of 3 pi over 4. Well, sine of 3 pi over 4 is square root of 2 over 2. So we can't do anything with that, so we leave it like that. Okay? So that's the slope. I'm sorry, that's the point. Now it's time for our slope. Slope is always dy dx. Right? So we know that's y prime of t over x prime of t. Or you can write it as dy dt over dx dt. Either way, these two mean the same thing. So y prime of t is 3 cosine t. X prime of t is negative 4 sine t. Right? And this is negative 3/4 cotangent t. All right. Now we need to find the slope at our point. At our point. So when t is 3 pi over 4. So we'll have negative 3/4 cotangent of 3 pi over 4. Cotangent of 3 pi over 4 is 1 over tangent of 3 pi over 4, right? So that's just 1. So we get negative 3/4 for the slope. So the equation of the tangent line is y minus the y coordinate is equal to the slope times x minus the x coordinate. That's it. Okay. Example 3. A curve is described by the parametric equations x is t squared plus t, y is t squared minus 3t plus 5. Part A, find the points of horizontal tangency. Point B, find the points of vertical tangency. Okay? So they're talking about, this describes a curve, all right? We want to know where on that curve do we have a horizontal tangent line and where on the curve do we have a vertical tangent line. Well, horizontal tangent means what is the slope? What is the slope of a horizontal line? 0, right? Vertical tangent is where what happens to the slope? The slope is undefined, right? Now think about what, when we're in parametric mode, what dy dx, write that here, dy dx is y prime of t over x prime of t. What would have to happen to make this 0? Y prime must be 0, right? Over on the vertical tangent side, how does this is y prime of t over x prime of t, undefined when what happens? When the denominator is 0, right? So we need to find the values, we need to find the points when y prime is 0, and we need to find the points when x prime is 0. Okay? So y prime is equal to 2t minus 3. Set that equal to 0. T is 3/2, right? So did we answer their question? Did we find the points of horizontal tangency? No. We found the time, but we didn't find the points. So we need to find the x and the y coordinates at those times. Or at that time. So x at 3/2 is 9/4 plus 2. 2 is 8/4. 8/4 plus 9/4 is 17/4. Right? No. I did that wrong. What did I do wrong? 9/4 plus, 3/2. 3/2, sorry. Okay, I don't know where I got that 2 from. I truly don't. 3/2 here. I'm glad I caught that. 3/2 is 6/4. 6/4 plus 9/4 is 15/4. Okay. Tell you what, the calculus is okay. The adding, not so okay. All right, y at 3/2 will be 9/4 minus 3 times 3/2 is 9/2 plus 5. Oh, more fun with fractions. My common denominator is going to be a 4. This is going to be 9 minus 18 plus 20. So that's 2/11/4. Okay, so the point where we have a horizontal tangent is 15/4, 11/4. Okay. Now over to the vertical tangent side. We find x prime and set it equal to 0. X prime is 2t plus 1. Set that equal to 0. And we have t is -1/2. So x at -1/2 is 1/4 minus 1/2. Okay, that's a -1/4. That one's okay for me. Y at -1/2 will be 1/4 plus 3/2 plus 5. More fun with fractions. 1/4 plus 6/4 plus 20/4. So 27/4. So the point where there's a vertical tangent is -1/4, 27/4. Okay. Fun with adding fractions. This is, hey, you know what? We should all do this every once in a while, right? You're like, no, we shouldn't. But anyway, yes, you should. All right, example 4. This is usually where I like to pause on day 1. If we've given a test that day, this is usually about a half an hour afterwards, so this is usually where I pause. But we're going to keep going. We're going to keep going to our day 2, all right, for this video. Okay, example 4. A particle moves in the xy plane so that at any time t, the position is given by this. Part A, find the velocity vector when time is 1. Well, velocity vector, I will use this vector notation like this. You don't have to. You can just call it v if you want, but it is a vector. Every chance I can to reinforce the idea that it's a vector, I'm going to do it. Because kids forget that we're dealing with vectors here. I don't know how many times on this test I've had kids, when I ask to find the velocity, they give me a number. Like, no, you're missing the whole point. That velocity, if we're on a curve, if we're in parametrics, the velocity has to be a vector. It has to have an x component, it has to have a y component. The magnitude of the velocity is a number, but the velocity itself is always a vector. And it's easy to find. It's just x prime, y prime. It's not hard to find, but it's not a number. It's a vector. So x prime is 3t squared minus 8t. Y prime is 4t cubed plus 6t squared. So the velocity vector at time 1 will be 3 minus 8, 10. And that's it. It's not bad at all. And yes, I have seen AP questions ask that. So, not bad at all. But you need to know that it's a vector, and you need to, you need to be able to find that. Part B, write the equation of the tangent line to the graph when t is 1. Okay, equation of the line. I need a point and I need a slope. So point. For the point, I need x at 1 and I need y at 1. I like plugging in 1 almost as much as I like plugging in zeros. 1 is not too bad. If I plug in 1, I get 1 minus 4, so that's a negative 3. Y at 1 will be 1 plus 2 plus 5, and that's an 8. So my point is negative 3, 8. The slope will be dy dx, right? dy dx, which is dy dt over dx dt, or you can call that y prime of t over x prime of t. Well, we did just find this up here, right? We found that that was 4t cubed plus 6t squared over dx dt, whoops, like that. And now we want to find it at time 1. And now I'm wishing that I had denoted it at 1. I don't want to have to rewrite it all again. So here's what I do. I come in and I just say at time 1, at time 1, at time 1. Then I don't have to rewrite the whole thing again. So at time 1, we're going to have 10 over negative 5, which is negative 2. Okay? So the equation will be y minus the y value is equal to the slope times x minus the x value. Not done. I mean, not bad. Okay. Find the acceleration vector when time is 1. Acceleration vector. At time 1, first find it at time t. So acceleration is the second derivative of x, the second derivative of y. So this is just 6t minus 8, 12t squared plus 12t, like that. So the acceleration at time 1 is the vector negative 2, 24. And that's it. A word about notation. For FRQs, you have got to say what you are doing to find the velocity vector. You've got to say that. Okay? You may not get credit if you don't say that. If you just come over and say the velocity vector is this, where did this come from? What did you do to get it? Remember, communication is important, all right? So if you write something and it's not crystal clear where it came from, you may not get credit for writing it, okay? You especially would not get credit if you just came over and did this without saying anything up on top. There would be absolutely no credit for that. These numbers came out of the blue. All right? You've got to communicate what you're doing. Get used to writing it. Get used to writing it. Same thing down here with acceleration. If you just write this, you have not communicated what you did to get that. So say it. It doesn't take long. Get used to doing it. All right? Okie doke. Next example. Example 5. Okay, a particle moves in the xy plane so that at any time t, with t positive, the position of the particle is given by this. Okay. Part A. Find the magnitude of the displacement of the particle from time 1 to time 3. Back, let me pull out, where is it? Back when we did just rectilinear motion, we said that displacement was the ending position minus the starting position. That was displacement. It just dealt with position. End minus start. Okay? So displacement here is different because our position is a vector now. Okay? So we want to measure the displacement or the magnitude of that change in position. Okay? So let me draw that. Let me draw a little picture. Let me get my orange out here. Let me see. So we are wanting to find out something like that length now. How do we find that length? Well, keep in mind that we always are dealing with components in particle motion and motion on a curve. We're always dealing with x and y components. So break it down into the components. This is delta x and delta y, right? So what is the length of that line? Pythagorean theorem, right? Delta x squared plus delta y squared. Okay? So magnitude of displacement, you're dealing with displacement. Okay? So that is our little formula. So the magnitude of displacement is the length of that line. So that is just the square root of delta change in x squared plus change in y squared. No integral, no derivative, just change. All right? So let's come off to the side and find change in x and change in y. Well, change in x will be x at 3 minus x at 1. End minus start. End minus start. So x of 3 is 9 plus 9. X of 1 is 1 plus 3. So the change in x, the delta x, is 14. Delta y is y at 3 minus y at 1. So y at 3 would be 27 minus 27, 0. Y at 1 will be 1 minus 3, so negative 2. So change in y is 2. So our displacement is the square root of 14 squared plus 2 squared. And I'm just going to say stop there. What about the magnitude of velocity? So that was magnitude of displacement. Magnitude of displacement. What about magnitude of velocity? Okay. Again, velocity is a vector. It's a vector. We want to find the length of the velocity, right? Length of velocity. It has components. What are the two components of the velocity vector? X prime of t, y prime of t. Those are the two components. So break these in when you're finding magnitude, break them into the components. That way you won't have to memorize things, you'll just know it. So this length, the magnitude or the length, will be the square of x prime plus the square of y prime. So the magnitude of velocity will be the square root of x prime of t squared plus y prime of t squared. So the magnitude of the velocity at time 1 will be the square of x prime at 1 plus the square of y prime at 1. Okay? So what is x prime and y prime here? Well, x prime is 2t plus 3. Y prime is 3t squared minus 6t Now we just put 1 in for t and write our answer. So x prime of 1 would be 5 squared. Y prime of 1 would be negative 3 squared. And we can simplify that if we need to, right? But I'm just going to leave it like that. All right. Magnitude of displacement, magnitude of velocity. I will tell you that you'll use this magnitude of velocity a lot because this is also speed. That is also speed. Okay. Example 6. A particle moves in the xy plane so that at any time t, the position of the particle is given by x of t and y of t. T is greater than 0. For what values of t is the particle at rest? Particle at rest. Okay. Well, back in rectilinear motion, the particle was at rest when the velocity was 0, right? That was when in rectilinear motion. Well, remember here that the velocity is not a number. The velocity is a vector. So the particle is going to be at rest when the velocity vector is 0, 0. When the velocity vector is 0, 0. So we need to find the times that make the two components both 0. So x prime of t is equal to 6t squared minus 30t plus 36. I'm going to set that equal to 0 and solve for t. I see a 6 in everything. And then I can factor this. And I get t is 2 and 3, okay? And now I'm going to come over and find y prime of t and set it equal to 0 because both of the components have to be 0. And remember, the two components of the velocity vector are x prime and y prime, right? So y prime of t is 3t squared minus 6t. Set that equal to 0, solve it for t, factor out a 3t, and I get t is 0 and 2. So at what time is the velocity 0, 0? Only at time equals 2. I see these as multiple choice questions, okay? So both components have to be 0, not just one. Number 7. Number 7, I'm checking the time here. I think I'll do one more, then that'll be a good time to stop. A particle moves in the xy plane in such a way that the velocity vector is this. Oh, this time we get the velocity vector. If the position vector at time 0 is 7, negative 4, find the position of the particle at time 1. We are given the derivative. We're given a position, so we can get any other position using the fundamental theorem of calculus, right? So first of all, they gave us the velocity vectors, so therefore they gave us x prime and y prime. X prime is 3t squared minus 4t, and y prime is 8t cubed plus 5. Yes, you have to say that, all right? They just said the velocity vector is this. They didn't say x prime is this and y prime is this. So you have to say those if you're going to use them. Okay? Now, we want the position at time 1. We have the position at time 0. So they are giving us x at 0 is 7. And they're giving us y at 0 is negative 4. Then they want us to find x at 1 and y at 1. Two first fundamental theorem of calculus processes. So I'm going to set it up. X at 1 minus x at 0 is the integral from 0 to 1 of x prime of t dt. Y at 1 minus y at 0 is the integral from 0 to 1 of y prime at t dt. So x at 1 minus x at 0 is 7 is equal to the integral from 0 to 1 of 3t squared minus 4t dt, right? So this is not a bad little integral. I'm going to go ahead and move my 7 over. Sometimes I wait, sometimes I bring it over now. Okay, so this is going to be t cubed minus 2t squared from 0 to 1. How nice that I gave you a 0 and a 1 to work with, huh? You're welcome. All right, put in 1, we get 1 minus 2, so that's a negative 1. Put in 0 and we get 0, so we just have 7 minus 1. So the x coordinate is 6. When time is 1, the x coordinate is 6. All right, come over and do the same thing for y's. Y at 0 is a negative 4. So y prime was our 8t cubed plus 5 dt. So this is going to be 2t to the 4th plus 5t from 0 to 1. So we have put 1 in for t and we get 7. Put 0 in for t, we get 0. So this ends up being 3. So the position at time equals 1 is, and I always like to use the same notation that they gave me in the problem. They used vector notation for the position, so I will give them vector notation for my answer. Okay. All right. That's a nice spot to stop at for today, and tomorrow we will finish these notes, and tomorrow's problems we'll have a calculator on, I think most of, if not all of them. Okay? So I will give you the assignment. It'll be part of that worksheet, and we will go from there. Okay.